Alright everyone, it's Mr. Reedy back with yet another video. Today guys, we're going to be talking about the integrated rate law, which is topic 3. And as a reminder folks, the rate laws we have discussed thus far have been comparing the rate of reaction to the change in concentration of the reactant or reactants, right? However, we often want to know the concentration of a reactant with respect to a specific time. So, guys, if we want to connect this to like a real world thing that we use kinetics in, would be looking at the concentrations of greenhouse gases in the atmospheres at any given time. So after, that gas has been produced for 10 years, what's its concentration now? Okay. And so that's the example that we have here, guys, is this is a greenhouse gas called a chlorofluorocarbon, short CFCs, okay? And chlorofluorocarbons, okay, they come from air conditioners and refrigerators, okay? And as you can see, their atmospheric lifespan ranges from 45 years all the way up to 1,700 years. And the idea, guys, is with these CFCs, right? We want to know, okay, if we're at year 62, well, then what's the concentration of, I don't know, trifluoroethane, okay? That's what we want to know. And so we would use kinetics to find this information specifically using the integrated rate law, which is the relationship between the concentration and a time for a chemical reaction. Now, in order to find this stuff, we integrate the rate laws from the previous lesson using calculus, okay? Calculus, of course, you guys aren't responsible for. We're going to wave the hands and the calculus is going to happen. It's going to be great, right? And then moving forward, we'll just have to be able to identify and use the proper rate laws when needed, okay? So consider the following reaction. Reactant A produces products, okay? And for a zero order reaction, we know the rate law is equal simply to the rate is equal to the rate constant, right? Where in the integrated rate law, we would have the concentration of A at T is equal to negative KT plus A naught, where A, the concentration of AT, is the concentration of A at any time. K, of course, is the rate constant. T is your time. And A sub 0 is the initial concentration of A. For a first order reaction, as a reminder, the rate would equal K times A, okay, the concentration of A. And the integrated rate law then is the natural log of A at any given time is equal to negative K times T plus the natural log of the initial concentration of A, where we know, of course, K and T are the rate constant and time respectively. For a second order reaction, we know the rate is equal to the rate constant times the concentration of A squared. So the integrated rate law would be 1 over the concentration of A at any given time is equal to KT plus 1 over the initial concentration of A. And guys, if you take a look at all of these integrated rate laws, they are all in the form of y equals mx plus b. And that's important because ultimately, since we have them written in the form of y equals mx plus b, we're going to be able to, of course, use simple algebra at that point to solve for the concentration, to solve for the rate constant, what have you, whatever we're missing, we can solve for it, okay? So, of course, your first value would be anything with the concentration of A at a specific time. That would, of course, be your Y. Your M is, of course, the rate constant. T is your X value. And then the y-intercept is your initial concentration of A value. Okay, so just keep that in mind. And let's dive right into an example. So it says, consider the equation for the decomposition of SO2Cl2. Okay, so SO2Cl2 forms sulfur dioxide and chlorine gas. And the problem says the concentration of SO2Cl2 is monitored at a fixed temperature as a function of time during the decomposition reaction, and the following data is tabulated. So again, guys, just like a running theme we saw in topic 2, we're being given data to evaluate here, okay? And that's very important. Again, kinetics is experimental driven. Almost all the problems we're going to see are going to have us using some form of data analysis. Now, when we're finding the integrated rate law, you can't do it by simply looking at a table. Okay, again, you can't do it by simply solving by looking at these numbers through a table. Instead, we have to use graphical analysis. And what we're going to do for this problem is we're going to graph that data 3 times. One assuming it's 0 order, the second time assuming it's first order, and the third time assuming it's second order. Okay, so this is what the graph would look like for a first order reaction. You can notice the way that I know it's first order, okay, folks, is that it says it's just the concentration of our reactant here, SO2Cl2. So since it's just the concentration here, that is our 0 order integrated rate law here. So what we're looking here, guys, for is essentially a R² value, or a correlation coefficient value closest to 1. So we're at 0.996. Pretty good. We'll see if another graph has a better R value for us. Okay, so this is us graphing the natural log of SO2Cl2 concentration versus time. You'll notice that I know it's the first order integrated rate law because it's the natural log version of it. And you guys can see our new line is given to us here. The R² value, or the correlation coefficient, is in fact 1. So this reaction, I can tell you right off the bat, is first order. Okay. However, we'll prove it to you by graphing the next graph, which is 1 over the concentration of SO2Cl2. You'll notice that the the graph here, again, the R² is not exactly 1, it's 0.996. So we know we have to go back to the previous graph in order to solve for the rate constant. But nonetheless, we have out an idea of what we need to do now. Okay. Again, how do I know this is the second order curve? The second order curve is, well, the second order integrated rate law is 1 over the concentration of the reactant at any specific time. Okay, guys, so now that we know that we need to use first order, right, so now that we know that we need to use first order, so our first order integrated rate law, again, is going to be the rate law that has the natural log in the equation. We basically have to pick any point in time or any trial rather to do this. Now, of course, this would be easiest if we just simply scroll back and we look at the table. So again, we're simply going to use the table here because why wouldn't we use the table? Okay. So let's take a look here, guys. Again, we're going to be using our natural log integrated rate law. So the natural log of, in this case, SO2 Cl2 is equal to negative K times T plus the initial concentration, the natural log of the initial concentration of SO2 Cl2. And guys, we're going to pick any, it doesn't matter at this point, we just have to be consistent in our trials. So why don't we go for this first trial? Okay, we'll just do at time 100 seconds. So the concentration of SN or SOCl2 is, of course, 0.0971. We're going to set that equal to negative K times the time at that point, which was 100 seconds. plus the natural log of our initial concentration, which was 0.1. Okay, and now guys, what I'm going to do is I'm just simply going to pause the video and simplify our algebra here. One thing you will notice, guys, is keep in mind that you have to be aware of your units. All right, units are important for the rate law equation, so don't forget them. Okay, but again, I'm just going to pause the video and simplify the algebra here. And for K, guys, I got a value of 2.94 times 10 to the negative 4 molar seconds. Okay, so that's our rate constant. And guys, I'm going to show you how we could use the shortcut. And if we go and graph the information in the first place, we can actually use the graph to get the same number. So bear with me as I bring the graphs back up. Folks, I just did make one minor error on the units here. The units should just be per seconds for the rate constant. It should not have had molar there, okay? But other than that, that's how we would solve this algebraically. Now, again, let's go take a look and see how it would have been easier just to use the graph. All right, everyone, as you can see, I have brought back the natural log of the SO2 Cl2 concentration versus time graph. Again, we're using this because we determined that the reaction is indeed first order based off our correlation coefficient being closest to 1. Now, again, I just wanted to show you guys how we could use this to determine the rate constant in a much faster sense. So this here, guys, this value here, again, if we were to write this, this would, of course, be y equals mx plus b. Okay, and we know for the rate law, this is simply going to be, well, the natural log of SO2, Cl2 is our y value, is equal, so this would be the y. And then we would have negative kT, so this would be m and x. And then, of course, plus the natural log of the concentration of SO2. And again, this is its initial concentration, so we do sub naught. So this would be the y-intercept. And of course, here, this is at time t. But nonetheless, as you guys can see, this value here, our slope, is negative k. So negative k is equal to negative 2.9 times 10 to the negative 4 seconds, which means the rate constant would just be positive 2.9 times 10 to the negative 4 per seconds. So I just want to point this out, that don't forget that this negative sign is here in the initial equation, and that's why we're getting a positive value for our rate constant for this specific one. Now, guys, personally, once you have determined what order the reaction is, so is it zero order, is it first order, is it second order, would you go back and use the data table that you graphed? Probably not. I just showed you that so you could see how the equation worked. Instead, you would just go right into looking at your graph because you have a line of best fit now. And since you have the line of best fit, it's easy to just look at the slope and see what your rate constant is, because your rate constant is in fact the slope. Just be aware of those negative signs with respect to the, of course, the equations. Okay, so let's continue on now. Here's a word problem. So it says a second order reaction has an initial concentration of 1 molar and a rate constant of 0.100 per minute. What is the concentration of A after 25 minutes? So this is a second order reaction. So we have to use this rate law on the bottom. So that's going to be 1 over the concentration of T at any given time is equal to KT plus the concentration of A at its initial concentration. Okay, so let's just begin to solve for this. So I'm going to plug in my numbers here. Okay, so I've plugged in my numbers, guys, just so everyone can see. And now I'm going to go ahead and start reducing. So the minutes will cancel out. And then 1 over the concentration of A at 25 minutes is equal to... Okay, so after some reducing, I got this side to reduce to 3.5. Now I'm going to solve for the concentration of A. And that will be this. So A at 25 minutes is going to equal to 1 over 3.5. And the concentration of A at 25 minutes is 0.29 molar. Okay. So guys, just a little bit of reducing there. But, once we find what equation to do, which again, in this case was using the second order integrated rate law, it was pretty much plug and chug. And then, of course, just using basic algebra to reduce the quantity until we get the concentration of A at 25 minutes. I would say the simplifying of this is probably the most difficult part of the problem. The chemistry portion of it's straightforward. You just have to be able to recognize what integrated rate law to use, then plugging your numbers appropriately. Like I said, it's more the simplifying that might trick you up here, but nonetheless, it's just that straightforward. Okay, let's continue on. All right, so we have another problem here. It says cyclopropane rearranges to form propene in the gaseous phase. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the negative fifth per seconds at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what is the concentration of cyclopropane after 235 minutes? All right, guys, take a moment, pause the video. But before you do, keep in mind that your units for time should be the same. Okay, so notice that you're being given minutes and seconds here. You have to pick one in order to solve this problem. So again, pause the video, try this one on your own, and we'll reconvene in just a moment. Okay, and I hope you got 0.0277 molar. Okay, the first thing you have to recognize is, of course, you need the second integrated rate law there with the natural logs, as this is a first order reaction. And then, guys, after that, you plug and chug. I opted to convert the 235 minutes into seconds when I was solving for this. So I multiplied negative 3.36 times 10 to the negative fifth times 14,100 seconds. I added that to the natural log of 0.0445, as you guys can see there. And then, guys, remember, in order to undo a natural log, you have to take the number e of both sides. So that's what I did here. Took the e of both sides. And then our concentration ended up being 0.0277 molar. Again, guys, I don't think the chemistry necessarily is going to be tricky in these problems. It's just going to be whether or not you have a certain level of algebra swag. And if you have some algebra swag, you'll find this pretty easy. Moving on. All right, so let's talk about half-life now. So half-life for a reaction is the time required for the concentration of the reactant to fall 1/2 of its original value. Okay, so here's just a graph illustrating it. We have it going through several half-lives here. So after 1/2, it took about 100 seconds. So if you were to count the particles, it'd be half the concentration. After 2 lives, that concentration would half again. And then after 3 half-lives, it would go again. Okay, so for the half-life for a zero order reaction is T1/2 equals the initial concentration of A divided by 2 times the rate constant. For a first order reaction, it's 0.693 divided by the rate constant. And for second order, the half-life is equal to 1 over K times the initial concentration. Okay. For nuclear decay or radioactive isotopes, we always assume first order kinetics. And for that matter, guys, although I may show the other equations, zero order and second order, in the class, only first order is evaluated on the AP exam. Okay, so this says molecular iodine dissociates at 625 Kelvin with a first order rate constant of 0.271 per second. What is the half-life of this reaction? So very simple, guys. It says it's first order, so we're going to use equation 2. Okay, so T1 half is equal to 0.693 over K. And I'm just going to plug in my value. So 0.693 divided by 0.271 per second. T1 half, or the half-life, is, and we get 2.56 seconds. And very simple there, guys. When it comes to half-life, as you can see, the math is very straightforward. Let's continue. All right, so here's more of a conceptual problem to half-life. So why don't you guys take a moment, pause the video, and see if you can determine the half-life picture for this particular reaction. All right, so pause the video and you try this one. All right, guys, I hope you chose choice C, as that is exactly where this particular reaction would go through its first half-life, because there are 10 particles in the initial phase, and by the time it's half of them have formed B, it was at 90 seconds. So the correct answer here is, of course, C. Okay, let's continue. It says a second order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reaction to fall between 1/8 of its original value? All right, guys, I want you to pause the video and try this one on your own. Alrighty, guys, and I hope you got the answer of 79.2 seconds. Guys, all I did to solve this problem is I kept taking successive half-lives until we were at 1/8 the concentration. So they gave us the half-life. So then I took the half-life again, so that would be a quarter of the concentration was at 52.8 seconds. And then I took the half-life again when presumably that was halved, and that would have been at the 1/8 of its concentration, which would have been 72.9 seconds. So again, all I did was take successive half-lives until we got to 1/8 of the original value. Okay, let's continue to our last slide of the day, which is just a summary of kinetics thus far. So the reaction order and the rate law must be determined experimentally. Okay, so that's the first thing. Second, the rate law relates the rate of the reaction to the concentration of the reactants. Third, the integrated rate law, which is when I wave my hands and calculus happens, relates the concentration of the reactants to time. The half-life is the time it takes for the concentration of a reactant to fall 1/2 of its initial value. Okay? The half-law of a first-order reaction is independent of the initial concentration. The half-lives of zero-order and second-order reactions depend upon the initial concentration. And with that being said, guys, that's the end of today's video. If you have any questions, please shoot me an email.